Hello, end of the night, late night. Time is 12:30. I said, fuck it, let's watch some Andrew Ng machine learning, and I want to sleep because why not? 30 minutes does miracle. We don't need to start tomorrow. We have one day ahead. We are one day ahead. Let's go. Let's go.
So here's one example. This is actually something I used to work on. I actually started a conference on still working on spam classification many years ago.
So it was about
It turns out that
in the middle of lecture 6 we are.
It's hard to
It was about who is the famous mathematician?
What to build a spam classifier. There are lots of things you could work on. For example,
Laplace, I guess.
Spam would deliberately misspell words.
Laplace estimate.
There's a lot of mortgage spam, right? Refinancing mortgage or whatever. But instead of writing the word mortgage, spammers would write M0 RT or instead of GAGE, maybe a //. Right? But all of us as people have no trouble reading this as a word mortgage, but this would trip up a spam filter. This might map the word to an unknown word.
So we are talking about spam, finding spams, how they work.
So that's one idea for improving spam. Well, actually, one of the PhD students, Hong Wei, actually wrote a paper mapping this back to words like that, so the spam filter can see the words the way that humans see them. Right? So that's one idea. Another idea might be a lot of spam email, spoofs email headers. You know, spammers often try to hide where the email truly came from by spoofing the email header, the email address often information. And another thing you might do is try to fetch the URLs that are referred to in the email and then analyze the web pages that you get to. Right? There are a lot of things that you could do to improve a spam filter. And any one of these topics could easily be 3 months or 6 months of research. But if you're building, say, a new spam filter for the first time, how do you actually know which of these is the best?
So yeah, machine learning and
my advice to
classifying as a spam or
let's just get this thing to work.
primary, for example, on Gmail can be a machine learning task. Very practical.
6 months on trying to analyze email headers, but just then implement a more basic algorithm, almost implement something quick and dirty, and then look at these
He winked.
the algorithm is still misclassifying. And you find that if after you've implemented a quick and dirty algorithm, you find that your anti-spam algorithm is misclassifying a lot of examples with these deliberately misspelled words. There's only then that you have more evidence that it's worth spending a bunch of time solving the deliberately misspelled words problem. Right? But if you implement a spam filter and you see that it's not misclassifying a lot of examples of these misspelled words, then I would say don't bother, go work on something else instead, or at least treat that as a low priority. Okay? So one of the uses of GDA, Gaussian distributed analysis, as well as naive Bayes, is that they're not going to be the most accurate algorithms. If you want the highest classification accuracy, there are other algorithms like just regression or
Naive Bayes are not highest quality.
Later, which will
Who expected them to be?
Accuracy in these algorithms. But the advantage of Gaussian distributed analysis and naive Bayes is that they are very quick to train, right? It's non-iterative. This is just counting, and GDA is just computing means and covariances, right? So it's very computation efficient, and also they are simple to implement, so it can help you implement that
So
quick and dirty.
easy to compute. Easy to compute.
And so I think for your project as well, I would advise you also to
Come on, finish it.
you know, as you start working on your project, I would advise most of
Takes like 40 minutes, but I think yeah, we will go all in. Let's finish this fucking.
Get a data set and apply something simple. Start with logistic regression, not a neural network, or not something more complicated. Or start with naive Bayes and then see how that performs. And then okay. All right. So that's it for naive Bayes and generative learning algorithms, the next thing I want to do is move on to a different type of classifier, which is support vector machine. Questions about this before I move on? Yeah.
Dude, this is student. I think it is the same student. Talks like.
Sorry, can you use logistic regression with discrete variables?
Did you hear that? Dude, mean 44. Go listen to it.
Can you use logistic regression?
And it says like Andrew asked, can you use logistic regression?
With discrete variables.
Discrete variable. Yeah. Discrete variable. Discrete variable. Dude, I have to bring water, right? And Andrew is like.
Oh, I see. Yeah, right. Yes. So yes, right. So one of the weaknesses of the naive Bayes algorithm is that it treats all the words as completely, separate from each other. Right? And so right, the words 1 and 2 are quite similar, and the words like mother and father are quite similar. And so, but with this feature vector representation, it doesn't know the relation to these words. So in machine learning, there are other ways of representing words. There's a technique called word embeddings. In which you choose a feature representation that encodes the fact that the words 1 and 2 are quite similar to each other, the words mother and father are quite similar to each other, the words whatever, London and Tokyo are quite similar to each other because of those city names. And so this is a technique that I was not planning to teach here, but that is taught in CS230. So in your networks. But you can also read up on word embeddings or look at some of the videos and resources from CS230 to learn about that. So the word embeddings technique, this is a technique from neural networks really, will reduce the number of training examples you need to learn a good text classifier. So it comes in with more knowledge. Anything else? By the way, I do this in the other classes too. In some of the other classes, somebody got a question, I go, oh, no, we don't do that. We just come back to CS229.
I missed the joke, by the way.
Actually, CS224N, I think, also covers this. Yeah, the NLP. Pretty sure. Yeah, actually, I'm sure they do. Okay. So, support vector machines, SVMs. Let's leave the classification problem.
Support vector machines.
Right, where the data set looks like this.
That's
and so you want an algorithm
messy.
to find, the nonlinear.
Yeah, non-linear. It's non-linear.
So the support vector machine will be an algorithm to help us find potentially very, very nonlinear decision boundaries like this. Now, one way to build a classifier like this would be to use logistic regression. But if this is x1, this is x2, right?
Change of variables.
Logistic regression will fit a straight line to
Yeah.
A Gaussian discrete analysis will develop a straight line decision boundary. So one way to apply logistic regression like this would be to take your feature vector x1, x2, and map it to a high-dimensional feature vector with x1, x2, x1 squared. X2,
I said change of variable.
x2, maybe x1 cube, x2 cube, and so on.
Oh.
A new feature vector called phi of x that has these higher dimensional features. Right? Now, it turns out if you do this,
I should not look at my phone. Fucking
to this
silence
feature vector, then logistic regression can learn nonlinear decision boundaries, with this set of features, there's just regression to actually learn the decision boundary. There's a shape of the ellipse. Right?
Oh yeah.
But manually choosing these features is a little bit of a pain, right? I don't know what I actually don't know what type of set of features could get you a decision boundary like that, right? Rather than just an ellipse, a more complex decision boundary. And what we will see with support vector machines is that we will be able to derive an algorithm that can take, say, input features x1, x2, map them to a much higher dimensional set of features, and then apply a linear classifier.
Of course,
Similar to logistic regression, but different in details.
Yeah.
That allows you to.
I don't think mathematically it's very difficult, but it's a good concept in machine
And I
learning,
think support vector
and we are going to learn it.
Actually, one of the reasons support vector machines are used today is a relatively turnkey algorithm. And what I mean by that is it doesn't have too many parameters to fiddle with. Even for logistic regression or for linear regression, you might have to tune the gradient descent parameter, tune the learning rate alpha, and that's just another thing to fiddle with. Where you try a few values and hope you get how you set that value. Support vector machine today has the very robust, very mature software packages that you just download to train the support vector machine on a problem, and you just run it, and the algorithm will kind of converge without you having to worry too much about the details. So I think on the grand scale of things today, I would say support vector machines are not as effective as neural networks for many problems, but one great property of support vector machines is turnkey. You kind of just turn the key and it works, and there isn't as many parameters like the learning rate and other things that you have to fiddle with.
Okay, support vector machine is also interesting. I think it doesn't have like crazy mathematics behind it though. I think it's just machine learning until now, which is like 6 sessions. It's not huge in depth. It's more terminology so far.
That we assume look like this and then are linearly separable. Right? And so the optimal margin classifier is the basic building block of a support vector machine. And we'll first derive an algorithm. They'll have some similarities to regression, but allows us to scale in important ways. That to find a linear classifier for training sets like this, that we assume for now can be linearly separated. So we'll do that today. And then what you see on Wednesday is, next Monday. Which is next Monday?
Wednesday is next one. Guys, I want to sleep. No, I don't want to sleep.
Maybe this is R2. And map it to a much higher dimensional set of features.
Oh, kernels. Wait, I think kernels are important. So x is in Rn, phi of x is in R. God knows what.
And then train an algorithm on this high dimensional set of features. And the cool thing about kernels is that this high dimensional set of features may not be R5, it might be R100,000, or it might even be.
Or is it manifolds?
Infinite. And so with the kernel formulation,
kernel, manifolds.
Set of features
kernel is a nice name. I want to know about it. No, I want to know about it.
Two-dimensional feature vector space into maybe.
Fuck it, I have to get lean, motherfucker. There is no cut to be shown.
It relieves us from a lot of the burden of manually picking features, right? Like, do you want to have square root of x1 or maybe x1, x2?
It's biceps.
You just don't have to fiddle with these features too much because the kernels will allow you to choose an infinitely large set of features. Okay. And then finally, we'll talk about the inseparable case. So we're going to do this today and then this next Monday.
Oh, we have cases that we cannot separate, even if we use R infinite as embedding a space. Sometimes it just doesn't work out.
And by the way,
And by the
the
way,
machine learning world has become a little bit funny. I think
it's funny, haha.
in the news, the media talks a lot about machine learning. The media just talks about neural networks all the time, right? You hear about
Neural network. It's not all machine learning. Logistic regression. It's simple, but it still matters.
Was a deep learning a little bit later in this class. But if you look at what actually happens in practice in machine learning, the set of algorithms actually used in practice is actually much wider than neural networks and deep learning. So we do not live in a neural networks only world. We actually use many tools in machine learning. It's just that deep learning attracts the attention of the media in some
Deep learning is hyped, guys. That's a good title for the video.
But they're not the only thing in the world. And so late last night I was talking to an engineer about factor analysis, which you learn about later in CS229, right? So unsupervised learning algorithm, and there's an application that one of my teams is working on in manufacturing where we use
Deep learning is hyped. My triceps are pumped.
Right? So there are all these other techniques that, including simple vector machines and
Pumped, hyped.
do get used and are important. All right. So let's start developing the optimal margin.
Yeah, why not? Who cares about the optimal? This guy knows. This guy is a practical.
First,
practical dude.
Functional margin, which is informally, the functional margin of the classifier is how confidently and accurately do you classify an example.
I do it with 120% confidence. What does it mean? What does it mean to do it confidently and
start by motivating this with logistic regression.
Logistic regression.
And so, if you turn this into a binary classification, if you have this algorithm predict not a probability, but predict 0 and 1, then what this classifier will do is predict 1. If theta transpose x is greater than 0, because theta transpose x is greater than 0, this means that theta transpose x is greater than and so predict 1 if theta transpose x is greater than 0, then the probability, the estimated probability of the possible 1 is greater than
10 more minutes. 10 more minutes and we're done. Seriously, I'm out of this shit.
This will happen if you have logistic regression output 1 or 0 rather than output a probability.
I'm just twisting my wrist.
In other words, this means that if yi is equal to 1,
Do you see that shit?
right,
I'm not loving doing this. Look at triceps.
that theta transpose xi is much greater than 0. This double greater than sign, it means much greater. Right? Because if the true label is 1, then if the algorithm is doing well, hopefully theta transpose x, right, will be faster than right, so the output probability is very close to 1. And if indeed theta transpose x is much greater than 0, then theta transpose x will be very close to 1, which means that it's giving a very good, very accurate prediction, very correct and confident prediction, right, that the label is 1. And if yi is equal to 0, then what we want or what we hope is that theta transpose xi is much less than 0, right? Because if this is true, then the algorithm is doing very well on this example. So,
I don't know where we did.
so the functional margin which we'll define in a second, captures this idea that the classifies a large functional margin means that these two statements are true. Right? To look ahead a little bit, there's a different thing we'll define in a second, which is called the geometric margin, and that's the following. And for now, let's assume the data is linearly.
You may say, I'm not focused, but guys, a low focus, low quality session at the end of the night is better than having nothing. So don't be hard on yourself. Just show up, watch the fucking video is the minimal thing you can do. Do it. Your mind will be set up for tomorrow, and each day you show up, you get better and better and better, and we learn machine learning. Suddenly look back, oh, January was over, but oh my god, machine learning, I learned it. Oh my god, coding, I learned it. Oh my god, it's not that difficult anymore. Oh my god, it's on my resume. Oh my god, we don't get rejected anymore. Oh my god, I can be a TA. Oh my god, damn. Oh my god, damn. Easy peasy.
Whereas the read line, has a much bigger.
I am going to run. Okay, geometric margin.
So even though the red line and the green line both.
It's talking about red line and green line. For all of you in Boston, what is the intersection of red line and green line?
Separation, which is called geometric.
Parker Street. Yes, yes. Parker Street. Yes, yes. Parker Street. Yes, yes. Parker Street. Yes, yes. Parker Street. Yes, yes.
And so, what I'd like to do in the next several, I guess, next 20 minutes is formalize definite functional margin, formalize definition of geometric margin.
So we have functional margin and we have geometric margin. And he wants to talk about them. Functional margin, geometric margin. We want to talk about them. Do 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 do. So notation.
In order to develop SVMs, I'm going to change the notation a little bit again. Because these algorithms.
I'm going to change the notation a little bit again.
I'm using slightly different notation.
Slightly different notation.
So when developing SVMs, we're going to use
SVM, guys. We are going to learn about SVMs. Learn about SVMs. We want to learn about SVMs. SVMs. We want to learn about this SVMs, SVMs. I want SVM, I want SVM. Do 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 do. I want SVM, I want SVM. Come on, I'll have output minus 1 and 1. G of Z as. Wait, what? It was minus 1 and 1, changed it to 1 and minus 1. If Z is greater than 0, G of Z is 1. So it is kind of a sine function, G of Z is sine function, G of Z is sine tangent, G of Z is sine function, G of Z. Previously on this show we had h theta of x, g of theta transplant, transverse. What is theta t? I don't remember. X transverse? No. H omega bx is g of omega tx plus b.
So for the SVM, the parameters of the SVM will be the parameters W and B.
Mm.
Once it's applied to X will be G of
So
this.
SVM has two parameters, theta, omega, and b, omega, and b. Drop x0 is 1. Drop it, drop it, drop it. We dropped it because we have b now. So there is no x0. There is no x0. B is theta 0. B is theta 0. Omega is theta 1 to theta. And
so this term here
is theta tx.
sum from I equals 1 through n plus p, right? So
Okay, I'm done. I'm done, Dean. I think we watched like 30 minutes. Well, let's watch 4 more minutes. My phone, my phone, my phone. Leave me alone. Leave me alone. My phone, my phone, my phone. Leave me alone. Leave me alone.
It's the definition of a
Functional margin. Okay. Oh, he's going to define it for us. Dude, look, 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 look. He could define it for us now, and tomorrow we are coming to the show, know what functional margin is, know how to use it, maybe no, but it's okay. We just, now I feel like a bit of resistance inside me to learn this definition, but assume how easy it will be tomorrow. My space is not working.
So the parameters W and B define the linear classifier, right? So the formulas you just wrote down, the parameters W and B defines a really defines a hyperplane.
Hyperplane.
Defines a line, or in high dimensions, it'd be a plane.
Line or high dimension.
Setting out the positive and negative examples. And so we're going to say the functional margin of hyperplane.
When we do chest, our shoulders hurt more. Why is that true?
So functional margin of a hyperplane defined by this with respect to one training example.
Is it his F?
To write as this.
F I had, or is it Y?
It just means straight line, right, within a high dimension. So it's just linear classifier, so it's just functional margin.
I know what hyperplane is.
We're going to define
what is the hat sign?
So if you compare this with the equations we had up there, if y equals 1, we hope for that. If y equals 0, we hope for that. So really what we hope for is for a classifier to achieve a large functional margin, right? And so, so if yi equals 1, then what we want, or what we hope for, is that W transpose xi plus b is much greater than 0. And if the label is equal to -1, then we want, or we hope, that this is much smaller than 0. And if you kind of combine these two statements, if you take yi, right, and multiply it with that, then these two statements together is basically saying that you hope that gamma hat I is much greater than 0, right? Because yi now is +1 or -1, and so y is equal to 1. You want this to be very, very large. It's -1. You want this to be very, very large. Negative number, and so either way, it's just that you hope this is
So if y is 1, wtxi plus b, we want it positive, very positive. And when y is negative, we want it very negative. And all the time, fi hat of I should be very positive, because it's the product.
So long as the function line.
Okay, I'm done. It's enough. Alright guys, thanks for staying with me. Here. Thanks for staying with me, because it was very boring. I had to go crazy. I know you do that too.